Every day, the components of any electronic device become smaller and smaller, and in the wake of this miniaturization, the JTAG interface has become increasingly important to manufacturers and software engineers. But hardware design engineers are often unaware of the value of JTAG for board debugging. Peter van den Eijnden is the president of JTAG Technologies, a company that develops and sells boundary scan products worldwide. And he joins us now with some great information about putting JTAG to use. Peter, welcome.
Thank you, Jim, for your kind introduction. Welcome, everyone, to this presentation about IEEE Standard 1149.1, also known as JTAG. Following a brief introduction to the standard and its basic operation, we will look at different applications and the advantages of using this standard. Traditional test and measurement equipment relies on connecting external probes, not readily possible given the state of the art of today's shrinking electronics. Since probing is often difficult, if not impossible, other methods must be used. This dilemma is best illustrated by the proliferation of BGAs, where the pins cannot even be seen, let alone probed. Other applications like software debugging with external in-circuit emulators are hampered not only by shrinking physical dimensions, but also by the increasing system speeds. IEEE Standard 1149.1 provides an elegant solution to this problem. The standard was developed by an international working group of electronic companies called the Joint Test Action Group, or JTAG. Hence, IEEE Standard 1149.1 is still often referred to as JTAG. The standard's official title is IEEE Standard Test Access Port and Boundary Scan Architecture. Since its release in 1990, many extensions have been defined in additional standards covering different signal types and applications. IEEE Standard 1149.1, or JTAG, defines the architecture for testing, measuring, in-system programming, debugging and monitoring on modern printed circuit boards without external probing. Chips compliant with this standard, called IEEE Standard 1149.1, or simply .1 compliant chips, contain additional logic and the JTAG interface to access this logic. The interface is called the Test Access Port, or TAP. It comprises of the four signals TCK, test clock, TMS, test mode select, TDI, test data in, TDO, test data out, and the fifth signal, TRST, active load test reset, which is optional. The boundary scan register, a register along the pins that is the boundary of a chip, is one of the crucial elements of the .1 standard. Devices containing JTAG logic are therefore also referred to as boundary scan devices. In normal operational mode, the core controls the pins of the chip. In test mode, the boundary scan register takes over the control of these pins. In this mode, the individual bits of the boundary scan register are used to drive and sense the device pins independent of the core of the chip. The boundary scan register for digital pins is defined in IEEE Standard 1149.1. The boundary scan logic for analog pins in mixed signal devices is defined in IEEE Standard 1149.4, released in 1999. And the logic for high-speed AC coupled digital pins in IEEE Standard 1149.6, released in 2003. The .4 and .6 standards are both extensions to the original .1 standard, and access to the logic is through the JTAG interface. .1, 4 and 6 together cover the majority of pins found on printed circuit boards. Besides the boundary scan register, a .1 compliant device also contains a bypass register. The bypass register is a 1-bit shift register that provides a minimum length serial pass from TDI to TDO in the chip. It can be used to speed access to data registers in other components on the board, as we will see later. Many more data registers may be included in the JTAG logic of a chip. The device identification register, containing information about the chip such as the manufacturer code, part number and chip revision level, is an example. A data register is selected through the instruction register. The JTAG logic of a chip is described in a so-called BSDL file that is supplied with the chip. BSDL stands for Boundary Scan Description Language and is also defined in the standard. Today's tools supporting this standard use the BSDL files to access the logic and for automatic test pattern generation. The tools handle the details of the logic such that users can focus on the actual applications without having to worry about or having a need to know the implementation details at chip level. In the remainder of this presentation, we will therefore focus on the use of the standard for various applications and its advantages. We will now look at the various applications of the standard. A generic board diagram will be used to demonstrate these applications. In this diagram, the boundary scan register is shown for the .1 devices. .1 devices are cascaded by connecting the TDI and TDO signals to form a scan chain. A single board may contain one or more chains, providing high-speed serial access to the test resources on the PCB. The first application that uses the boundary scan register is structural testing. This test method focuses on the test of connections between different chips on a printed circuit board. Structural testing has the following advantages. Known testability, what can be tested. Known fault coverage, what is actually tested. Automatic generation of tests and immediate detailed pin-level diagnostics are available. The most simple example is a continuity measurement to check the connectivity of a particular connection. This so-called buzz or ring measurement is frequently used in R&D as well as manufacturing repair and field service repair. Traditionally, a multimeter is used to ring out a connection. Using boundary scan, this measurement can easily be performed by selecting the drive pin and sense pin. A connection is present between these pins if a specific stimulus applied at the driver is seen by the sensor. Unlike a bus measurement, which tests one connection at a time, an interconnect test tests all connections between boundary scan devices simultaneously. By combining external boundary scan devices, also off-board connections can be included in this test. An interconnect test can be generated automatically and is generally used in production. Also, the connections of devices that have no boundary scan themselves, but are surrounded by boundary scan devices, can be tested using the boundary scan registers of those surrounding devices. This is referred to as cluster testing and can be used to test random logic, memory interconnect, and interconnect of complex peripheral devices. Also, cluster tests can be done interactively or can be fully automated. To simplify the testing of their interconnects, future memory devices may contain special test logic as defined in a new standard that was released earlier this year. IEEE Standard 1581 for Static Component Interconnection Test Protocol and Architecture. To test very high-speed signals at speed, built-in self-test logic or BIST logic contained in associated devices can be accessed through the JTAG interface as described in the .1 standard. A second application of the standard is in-system programming, used to configure flash memories as well as programmable logic devices after these have been mounted on a printed circuit board. In-system programming offers the following advantages. No programmed devices in stock, resulting in simpler logistics for these parts. Customizing a product at the end of the production line. Less risk of bent leads. And in-system programming can be on the same station as test, resulting in less handling. Also, reprogramming in the field for field upgrades is easily possible. Flash memories can be programmed via so-called bus emulation. Address, data and control values are shifted into the boundary scan registers of surrounding devices and then applied in parallel to the flash. In this way, memory read and write cycles are emulated. Unlike flash memories, programmable logic devices such as CPLDs and FPGAs can be programmed directly through the JTAG interface without requiring additional devices. This is often referred to as JTAG programming. The IEEE standard for in-system configuration of programmable devices, IEEE standard 1532, describes the data registers and programming instructions that define a standard methodology for configuring programmable devices through the JTAG port, or the 1149.1 tab. Standard 1532 also defines an extension to BSDL, facilitating standardized automation tools for device programming. Microprocessor debugging is a third application of the standard. The debug logic built into modern microprocessors provides the ability to load, run, hold and step the CPU and enables the software engineer to debug CPU code via the JTAG interface. The debug logic can also be used to test the processor kernel of a board, a method known as emulative test. For devices like microprocessors, it may be desirable to control the power consumption of the debug logic or to quickly access a specific IP block on a system-on-chip device to improve the software debugging performance. This additional functionality is defined in IEEE standard 1149.7 and can be accessed through the JTAG port, or, alternatively, through a reduced pin count tab defined in .7. The official name for .7 is IEEE Standard for Reduced Pin and Enhanced Functionality Test Access Port and Boundary Scan Architecture. This standard was released in 2009 and complements the .1 standard with which it is backwards compatible. Besides microprocessor debug logic, other types of internal instrumentation is built into devices for chip internal test and measurement purposes. To facilitate the use and reuse of these instruments at board and system level in a standardized way, a new standard, IEEE 1687, or IJTAG, is currently under development. This standard for access and control of instrumentation embedded within a semiconductor device will describe the methodology for access to the embedded instruments through the JTAG port, and will provide a standardized description format how to operate the instruments. Like .4 and .6, also this standard is an extension to the original .1 standard. R&D, manufacturing and field service all benefit from using this technology. It makes test and measurement and in-system programming on modern, very fine pitch boards possible at low cost and at all stages of a product's life cycle. A single instrument that provides the interface between the JTAG port on the target board and the PC can control the various applications we have seen before, as well as future applications resulting in low-cost capital investments. While R&D and field service often use interactive software tools, full automation is available for applications in manufacturing. In manufacturing, the low cost of JTAG, structural testing and in-system programming furthermore makes the technology applicable for the entire range of production, from very small series to high-volume mass production. The fact that all manufacturing applications can be handled by a single tool not only limits the capital investment, but also results in less handling of boards. Depending on organization and requirements, the JTAG tools can either be used as a standalone station or can be integrated with your functional test stations, thus saving extra fixtures and board handling. For boards on which not everything can be covered by boundary scan, you can integrate the JTAG tools with your existing in-circuit tester or flying probe tester. Such integration helps you to reduce the cost of fixtures, less probes, and reduces the amount of board handling. The amount of recurring test costs during production depends on the testability of a board and hence is already determined during its design. Boundary scan provides an excellent opportunity to limit the recurring test costs of a printed circuit board. By taking a few simple design for test rules into account, different test and programming applications can easily be created and can be used efficiently in manufacturing as well as field service. Closely watching the testability of your design and fault coverage of your tests not only limits those test costs, but also helps to get products to market faster with higher quality levels. A complete overview of design for test rules at board and system level can be found in our DFT booklets. Both are available for free through our website jtag.com. Thank you for your attention. Back to you, Jim.
Well, Peter, I've got a few questions we've collected here, so let's see if we can get some answers to them. I'm sure you can provide them. This first one asks, in what markets is boundary scan most likely to be used?
Well, Jim, electronic companies worldwide in all segments can use boundary scan. This is because the technology is independent of the application. Boundary scan is used in markets like defense, automotive, datacom, telecom, consumer electronics, and so on.
Our next one says, what departments within a given company are most likely to use boundary scan?
Well, Jim, boundary scan can be used in research and development, production and field service. In research and development and field service, for example, a tool to ring out single connections is already very valuable. Also, tools for in-system programming are frequently used in those departments. In manufacturing, fast testing and board programming are paramount.
All right, this one asks, is there a long learning curve for the use of boundary scan?
That is both an interesting and challenging question, Jim. There are two aspects to this question. The first is implementing boundary scan in your design. To exploit the capabilities of boundary scan to its max, DFT rules should be applied. These rules are generally easy to learn. But of course, if boundary scan is new, then some points can be overlooked. Therefore, we offer services such as design reviews to help new users to quickly adopt these rules. The second aspect are the tools. Since these hide all details of boundary scan and are intuitive and easy to use, learning the tools is straightforward, and when coming back to the tools after some time, there is no relearning. All in all, the learning curve for boundary scan is short.
All right, Peter van den Eijnden of JTAG Technologies, we need to wrap things up, and I want to thank you for taking the time to be with us here today for our event.